Hello, good day everyone. I am creating this video because I had difficulty recording our session during our face-to-face sessions. So I'm doing this in order to cover three topics regarding history of computing, particularly the design and programming of the analytical engine invented by Charles Babbage during 1837. So basically, we will start with the design of the analytical engine. The analytical engine is a mechanical computing device which which is different from the previous computing devices in the sense that there will be two types of inputs. In the previous devices like the step reckoner and the arithmeter, the input are just a set of data that are used in identified arithmetic operations. In the case of the analytical engine, the input consists of both formula and data, which are provided by punch cards using Jacquard's loom. The machine itself could also be able to do punches onto the cards, which are going to be read later. It uses an ordinary base 10 or decimal fixed point arithmetic. An important component of the analytical engine is called the store. This signifies or symbolizes our modern notion of a memory. The store then is capable of holding 1,000 numbers of 40 decimal digits. Third component is called the mill, which is typical of our modern arithmetic logic unit and the central processing unit. The mill would be able to perform arithmetic operations. It can also do comparisons and square roots. Like the central processing unit of a modern computer, it has its own sets of commands or internal procedures to carry out some of the more complex instructions specified by a user program. There's a diagram in our Diggler site representing this analytical engine. Okay. The actual figure looks like this. Okay. This picture is a simplified version created by Charles Babbage. Instead of being a 40 digit computer, it uses the actual prototype only processes 20 bits, or rather 20 decimal digits. And a symbolic diagram is shown in our uh, reference. The analytical engine mill or the mill itself is composed of a column of gears where each rotating gear can be used to, to store a decimal symbol from 0 to 9. In this case, there are 40, so there are 40 rotating gears in each column. There are two sets of columns, an ingress column or an egress column. So the ingress set is also composed of three subcolumns such as the prime ingress axis 1, ingress axis 1, and ingress axis 2. Uh, Ingress axis 1 and ingress axis 2 is where the inputs are stored. For example, during plus operation, the first addend is in ingress axis 1 and the second addend is in the ingress axis 2. Uh, During the multiplier is on ingress axis 1 and the multiplicand is in ingress axis 2 or vice versa. The egress axis is called egress because it is used to store the output. During normal mathematical operations, the result is stored in the egress axis, except during division, where uh, the egress axis is used to store the remainder, and the quotient is stored in the prime egress axis. In case of large numbers, large inputs, the prime ingress axis 1 is used to store the excess values or the remaining values from the ingress axis 1. And programming the analytical engine entails using programming cards, and the programming cards are classified into different classes. The most common type of card is called operation card. We can distinguish the operation card because the operation card can have four basic symbols. They can be used to store symbols representing a specific arithmetic operation, such as plus, minus, times, and divide. There can also be combinational cards, which are used to perform conditional jumps or repetitions in a program. They are called conditionals because the conditional jump or looping can be executed only when a specific condition is satisfied. Special cards are cards that are used to halt the engine or stop the program, ring a bell, or give comments to the engine operator. Normally, the bell special card is used at the end to signify to the operator that the whole operation has finished. Another type of card is called the number card. The number card is our typical representation of the modern assignment statement because in a modern programming language, you can store a value to a variable. So say when in C++ or C you say x equals 10, we are storing the value 10 in the variable x. However, in the analytical engine, variables are not assigned variable names. They are assigned uh, addresses. So in particular, they are assigned numbers. For example, the first variable is variable 0. The second variable is 001 up to variable 999 because the analytical engine was designed to have 1000 1000 number store, which means that 1000 decimal numbers can be stored in its memory. So number cards are like assignment statements. They are used to assign values to variables in the analytical engine store. Variable cards are data transfer cards. They are used to fetch values from uh, the store into the mill. So normal variable cards are used to transfer from the store to the mill or from vice versa. The machine can either erase the number during or a destructive read or let it remain as it is or add an indestructive retrieve. Special variable cards are used to punch values or results to a card or read a value from the card instead of the store. So what do they look like? Operation cards require four holes, one for each designated mathematical or arithmetical operation. Number cards require 50 columns of 10 possible punches to represent 50-digit numerals, no? The 50 columns, and plus one extra column to signify whether the number is positive or negative. Variable cards can have one of the five possible punches, representing whether a number should be read from the store and erased to be to be erased in the process. It can be read from the mill and to be put to the store or the other way around. Here are example programs from the analytical engine. So N001 is a number card. N represents the number card and the number 001 specifies the address in the store. In our modern terms, we refer to 001 as our variable name or variable number. So N001 specifies where the number should be stored, like an index in an array. L001 means load the value into the ingress axis. Remember that uh, the ingress and the egress axis serves as the registers. When you say L001, we are trying to load the store 001 to the ingress axis. Now the convention is usually there are two loads. The first load stores to ingress axis 1 and the second load stores to ingress access 2 automatically. S002, which is a variable card, stores the value this time of the egress access into the specified value in the store. For example, in this case, whatever the value of the egress access is, will be transferred to address 002. In case of division, we can say S002 prime, because in division, the quotient is stored in the prime egress axis, unlike the other operations where the egress axis is used. So when you store 002 prime, you are storing the prime egress axis into address 002 in the store. P is a special operation to print the card, the last result of the egress axis, into a card. H stands for halt the engine, to stop the engine from running. There are also combinational cards CB and CF. For each combinational card, you can have a conditional combinational card and a unconditional combinational card. We can distinguish a combinational card or a conditional card from a conditional one because of what follows the CF or the CB. CF question mark means conditional. CF plus means unconditional. In this example, when you say CF question mark 5, we mean move forward. F stands for count forward 5 times from the current location. The current location is the location after the current command, if the stand-up lever is set. Otherwise, it will just continue normal sequence if the stand-up run-up lever is not set. What is a run-up lever? Run-up lever is like a toggle switch, which is automatically set or reset by the analytical engine depending on the sign of the egress axis. If the sign of the egress axis is different from that of the sign of ingress axis 1, then the run-up lever is set. That's very important to remember. Only when the signs of ingress axis 1 and the egress axis are different where the run-up lever is set. Otherwise, it is reset or its value will be 0. May question ako sa inyo. Ang basic value CB5 is the same as above, but will go backwards if the run-up lever has been set. Here are examples. N001 500, this puts the value 500 to store 001. N002 30 puts the value 30 to N002. Okay. Divide L001 and L002. Divide sets the machine to divide, and loads the number at 001 in the ingress axis 1. The second load automatically loads into ingress axis 2. In the next video, I'm going to show you an actual program and demonstrate how the analytical engine works. See you then.